For today's lecture about molar mass, we are going to be using the periodic table, and this is found up in the resources. Make sure that you have either printed this or that you are able to kind of have it handy because we're going to be using this a lot. The molar mass is the mass of 1 mole of a substance. It's actually equal to that substance's atomic mass measured out in grams. Where do we get this number from? Well, if you look at the periodic table and you look at carbon, for example, 12.01, that measurement, if you remember back to when we talked about isotopes, was the average atomic mass units of all of the different isotopes of carbon, right? Remember, we had some carbon that had 6 protons, 6 neutrons. So it had a total atomic mass of 12. We had some that had 6 protons, 7 neutrons. So an atomic mass of 13. And then if an average, so we have an average atomic mass unit for carbon was 12.011. That's where that number came from. So that's our symbolic, what our periodic table tells us. That 12.011 atomic mass units, that's what the periodic table says.
So therefore, we refer to the periodic table to find the molar mass, which is how much 1 mole of a substance weighs in grams. So 1 mole of sulfur has a mass of 32.065 grams. Now I want you to think about 3 different candies here. Let's say that I have 10,000 M&Ms, 10,000 jelly beans, 10,000 chocolate malted balls. So I have the same amount of each of these different candies. But notice that 10,000 M&Ms weighs just shy of 9,000 grams. 10,000 jelly beans, whoa, is quite a bit more, just over 27,000 grams. But man, 10,000 chocolate malted balls is 154,000 grams. So I can have the same amount of substances, but they weigh very differently. Similar to, let's say I had the same amount of sulfur, 6.02 times 10 to the 23rd sulfur atoms. So let's say I have 1 mole of sulfur. Let's say I have 1 mole of carbon, 1 mole of zinc. Notice that they all have a different mass. I can have the same amount of substances, but they have different masses. And again, I can see what those masses are based on that AMU, average atomic mass units, on the periodic table. So why don't you take a second and see if you can find the molar mass for the following elements. Did you get the following? Great.
If I were to take 6.02 times 10 to the 23rd atoms of carbon, so now we're thinking at the particulate level, okay? If I had that many atoms of carbon, which is equal to 1 mole of carbon, if I took that many atoms and I put it on the scale, so now we're thinking we're in the lab setting or in real life. So that's the macroscopic level. In real life, if I were to put it on a scale, it would weigh 12.011 grams. So do you see the connection that we can get the mass of 1 mole of something right from the periodic table? What's also kind of cool is we're able to, by doing this, we're connecting the macroscopic measurements from the scale with particulate counts, because we have 6.02 times 10 to the 23rd atoms, and we're able to connect it to the periodic table, the symbolism aspect of it. Here's a picture of 1 mole of a bunch of different substances. We can see 1 mole of mercury 2 oxide, 1 mole of sucrose, 1 mole of sulfur, 1 mole of copper 2 sulfate pentahydrate, 1 mole of sodium chloride, 1 mole of copper. Notice that they all have what looks like different amount, but that's not the case. There's all the same amount. There are 6.02 times 10 to the 23rd atoms of each of those substances, and they all weigh differently, but they're all 1 mole of something. It would be like if I said I had a dozen eggs and a dozen cars. Okay, so we still have the same number of eggs and cars, but they are going to weigh differently and they will take up a different amount of space. Same is true with chemicals and compounds.
So the molar mass is the atomic mass of any substance expressed in grams. So we say that that's the molar mass of a substance. The atomic mass of carbon is 12.011 AMUs. So therefore the molar mass of carbon is 12.011 grams for 1 mole of carbon. Now nitrogen, if it's by itself, is in Brinkelhoff, right? It's a diatomic molecule, N2. So the molar mass of N2, we would need to add up 2 nitrogens. So 14.01 times 2, which would be 28.02 grams per mole.
Let's look at another example. Magnesium. If we look at the periodic table and we see magnesium, it says on the periodic table that its average atomic mass units is 24.305. Now we can take that and we can say, all right, well, so 1 mole of magnesium, which is equal to 6.02 times 10 to the 23rd atoms of magnesium, is also equal to 24.305 grams of magnesium. And what's great about seeing these equalities is that we can make conversion factors because of this. Remember when we said that 12 inches was equal to 1 foot, we could also say that there's 12 inches per 1 foot, or in 1 foot there was 12 inches. And we would take this and we would say, okay, which one of these am I using, this conversion factor or this conversion factor? So we're going to do the same thing for this. One more example, sulfur. Look at the periodic table and it says it is 32.065 AMUs. Remember, that's an average of all of the isotopes of sulfur. Okay, then we also know that 1 mole of sulfur is 6.02 times 10 to the 23rd atoms of sulfur, which is equal to, if I put it on the scale in the lab, 32.065 grams of sulfur. So we're able to then take this and I can convert from moles to grams or grams to mole.
What if I have a compound? Well, in that case, I just sum the molar masses of each element. For example, if I wanted to find the molar mass of morphine, which is C17H19NO3. Morphine is commonly used to treat severe pain, and although it is highly addictive, tolerance develops with long-term use. So therefore, I would need to take carbon, find out what carbon's molar mass is, and times that by 17. Find hydrogen's mass, times that by 19, because there's 19 of them. There's 1 nitrogen, and there's 3 O's. Add them all up, and that would be 285.313 AMUs, which means that its molar mass is 285.313 grams per mole. Why don't you pause the video right here and see if you can find the molar mass for ammonium gas, sulfur hexafluoride, and magnesium nitrate. Did you get the following answers? Great. Now, what is the mass of 1.33 moles of titanium? We want grams, we have moles. Let's set it up starting with my moles of titanium. And again, I need to use a conversion factor. What do I want? I want grams of titanium. What have I got? I've got moles of titanium. So for every 1 mole of a substance, we look at the periodic table to figure out how many grams there is. So in this case, 1.33 times 47.867 to get 63.7 grams of titanium. I started with 3 significant figures, so I'm going to end with 3 significant figures.
So let's say that I have 11.55 moles of carbon. How many grams is that? I always start with what I'm given. So I'm going to write down 11.55 moles of carbon. Now I want to get from moles of carbon to grams of carbon. I know that 1 mole of carbon, if I look on the periodic table, it tells me that there is 12.011 grams of carbon for every 1 mole of carbon. All right, so then I'm going to take this and I'm going to make my conversion factor. So I can say 1 mole of carbon, there is 12.011 grams of carbon, or in 12.011 grams of carbon, there is 1 mole of carbon. So then I'm going to take this, instead of saying equal, remember we're going to say or. Which one are we going to use? Well, here I have moles of carbon on top. I need to have moles of carbon on the bottom to cancel out, and grams of carbon on top, because what do I want? How many grams? Remember, it's what you want over what you got. What you want, I want grams of carbon. What have I got? I've got moles of carbon. So I need to use not this one, I want this. So I'm going to write my 12.011 grams of carbon for every 1 mole of carbon. Now my calculator tells me that the answer will be 138.72705 grams. But we need to remember our significant figures and look at how many sig figs did I start with. And here I started with 4 sig figs. So I need to finish with 4. So I'm going to count 1, 2, 3, 4. Does my 2 do anything to that 7? No. So my final answer will be 138.7 grams of carbon. And then circle your answer. All right, let's do another practice problem. Calculate the grams of the mass of 0.750 moles of water. Okay, so let's start with our 750 moles of water. Okay, so we need to figure out for every 1 mole of water, what is the mass of that? So we need to look at my periodic table and say, all right, we need to figure out what 2 hydrogens and 1 oxygen has a combined mass of. So I'm going to go, okay, my hydrogen is 1.0079. I'm going to times that by 2. And I'm going to add an oxygen, which this periodic table says 15.9994. So my mass of H2O is 18.0152 grams. All right, and it's okay if you just have 3 decimals or 4 decimals. When you get to the very end, it's not going to matter, because if you look, we're only going to be significant to 3 sig figs anyways. So that extra couple of decimals won't change. I have just been using the numbers from this periodic table. All right, so again, we know that we can take this and we can write 2 conversion factors. We can have our 18.0152 grams down here, and we can have 1 mole of water down here. And we're going to use one or the other. So because I'm starting with moles of water and I want grams, remember, it's what you want or what you got. I got to get rid of my moles of water, and I want grams of water. So my gram, we got to use this guy. My 18.0152 over 1 mole of H2O. And when we plug it into the calculator, we get 13.5114 grams of water. I'm going to check my significant figures. Again, we started with 3 sig figs. Oh, that's multicolored. And I'm gonna go, all right, 1, 2, 3, draw a line after that 5. That 1 is not going to change my 5. So that's 13.5 grams of H2O. Make sure you label it. Now I'd like for you to pause and try to do this conversion. We want, this is 2 parts. How many moles is this? And how many molecules is this? See if you can work this. Okay, so first thing I had to do was I had to look at the periodic table and figure out the molar mass of calcium phosphate. So I did that by saying, okay, I've got 3 calciums, 2 phosphoruses, remember that distributes, and 8 oxygens, and multiplied it by their AMU on the periodic table to get the mass of 1 mole of calcium phosphate. Okay, so to figure out which conversion factor we need my grams on the bottom and 1 mole of calcium phosphate on top. So I need my grams on the bottom. And when I plug that in the calculator, I get this really small number, which makes sense because we know that 1 mole of calcium phosphate weighs 310 plus grams. So if I only have 6 grams, it's going to be a small fraction of that 310. So let's look, and I've got 3 sig figs here. So I'm going to count to 3 sig figs here. 1, 2, 3. That 4 is not going to change my 3. So I will have 0.0193 moles of calcium phosphate. Then the next step is how many molecules is this? So once I know how many moles, we know that 1 mole of anything is equal to 6.02 times 10 to the 23rd molecules, or atoms, or particles. So I'm going to take my 0.0193 moles of calcium phosphate, and I'm going to have moles on the bottom. 1 mole is equal to 6.02 times 10 to the 23rd. And my calculator tells me that it is 1 point, again to 3 sig figs, 1.16 times 10 to the 22nd molecules of calcium phosphate. Make sure you are labeling all of these. Make sure you're watching significant figures, and make sure that you are using the right conversion factors.
This one wants to know what's the mass of 2.55 times 10 to the 23rd atoms of lead. I've got atoms, and we know if I have atoms, I can't go directly to grams. So this is going to take us 2 steps. How would you go about setting that up? Well, I would need to go, let's think about the pathway. Atoms, we need to go then to moles, and then moles to grams. We know that if I'm starting with atoms, I got to have atoms on the bottom. And we know that there's 6.02 times 10 to the 23rd atoms in 1 mole of anything. And therefore, those will cancel. I then have to have moles of lead on the bottom. And we know that for 1 mole of anything, we look at the periodic table to see how many grams there are of it. I started with 3 sig figs, so I need to end with 3 sig figs. Let's see if you can go the reverse direction. How many molecules are present if I have 2.25 grams of fluorine gas? Now remember, fluorine is one of those diatomic molecules when it's by itself. F is in Brinkelhoff, and so it would be F2. I'm starting with grams. Grams I need to get to moles, and from moles I can get to molecules. Did you have it set up correctly? Grams to moles. And again, in 1 mole of F2, I have to add up 2 fluorines worth of mass. And then in 1 mole of F2, we know there's 6.02 times 10 to the 23rd particles, or molecules. And wrapping it up, I have 3 practice problems for you to try setting up. So pause the video here, and I will put the answers up in just a second. How did you do? How do you feel converting from mass to moles to molecules and from molecules to moles to mass?